What up, everybody? We're just doing entry 3 here, talking about dilutions and solubility curves. This is a topic that I have simplified a little bit since we moved to online learning. So we'll get some good background here and we'll move forward, specifically with solubility curves. Dilutions is pretty straight ahead, or straightforward. So why do we need to know how to do dilutions? If you click on this YouTube link right here, it's just a different person talking about concentration and dilutions. It's a good bonus for you. You don't have to watch that, but it would be useful for you in that context. So really, if I were to buy certain contents online, you can only get the acids, as an example, as a really concentrated version. So they can sell you a really concentrated or high molarity solution. But the reality is, if I were to use it, it'd be too strong to do for a lot of labs. So I need to dilute them, and this is a process I would go through them. There's also a way that you can figure out, as an example, how much bacteria are present by going through a process of serial dilutions. Normally we do a lab with that in class, but since we don't have class, that we're not really doing that. That's called serial dilutions. There's also a process of dilution that you could talk about with essential oils. So if you go to the presentation, you could certainly click on that link and read about that as well. So what's the dilution equation? M1V1, M2V2. M is molarity, V is volume, and the ones just tell you initial and final, where you're starting and where you're ending. So if I know 3 of these 4 variables, I can solve for the fourth. It's just algebra, multiply and then divide. So volume can be in liters or milliliters. It doesn't matter. They just have to be the same. So in all these problems, you'll be given 4 variables, and then or 3 of the 4 variables, and you just have to find the fourth. So it's multiplied by 2 and divide by the other one that you're given. It's really that straightforward. So let's look at a few example problems. The main idea for the example problems is that when I see the word of, that tells me that those 2 variables are connected. So what volume of 2.5 molar must be diluted to get 250 milliliters of 0.75? So these 2 are connected. Those are the 2 that I'm going to multiply, and I'm going to divide by the third. Normally your starting point is going to be the more concentrated acid. So that's another way to think of it that way, and your lower volume. So you could think of them, the paired ones as your ones. It doesn't really matter because you're always going to be multiplying and dividing. Let's just look at some examples. That might be the easiest way to do this. So what volume of 2.5 molar must be diluted to get 215 milliliters of 0.75 molar solution? So these are where I'm ending, and that's my starting position. So what I'm solving for here is my initial volume. But if I notice that these 2 are connected, I could just multiply those 2 and then divide by 2.5. So it's 0.75 times 215 divided by 2.5 is going to give me 64.5 milliliters. So now if I needed this to do a lab, I can go measure out 64.5 milliliters of 2.5 molar solution, and then dilute it down to 215 and know what the concentration is. Hey, think about the context of orange juice, right? If you ever bought juice from concentrate, it just means that they concentrated it down, right? They made a really strong juice, and then you add water to it, you dilute it in order to get the juice that's drinkable. Okay. So here, maybe pause for a second and try to figure out which variable goes where. If you notice, it says final volume of 1500 milliliters. That's my V2. That means that's my V1. That's my M1. So I just plug in M1 and V1. I'm solving for my second concentration. So you're multiplying these 2 and then dividing by your third variable to give me 2 molar nickel sulfate. Okay, next example. Pause here to see if you can figure out what goes where. And 850 of 0.5, I know those 2 are going together. And it's just saying those are my second ones because what volume of 5 molar? I'm starting with a more concentrated solution. So that means to solve for my initial volume, I multiply these two, divide by that one. 0.5 times 850 divided by 5 gives me 85 milliliters. And there's a couple extra practice problems, and the key will be posted online as well. This hopefully is a topic you don't need a ton of practice with, but we're going over it. And if you have questions, certainly ask me. The last part, we're going to talk about solubility curves from a general perspective. I'm going to connect it back to what we've talked about already, and then we will move forward. So solubility, remember, is connected to polarity, right? So two substances that mix are called miscible. Two substances that don't mix are called immiscible. So we've assumed that all substances do mix, but the reality is that unless they have the same polarity, they don't mix. And that's what we saw in this here. I have a ionic salt mixing with a polar water molecule, and it mixes. Here I have oil, nonpolar, water, polar. They don't mix. I can shake them and force them to mix a little bit, but they will eventually separate. So not all substances mix. But even if they do mix, there's factors that impact how well they mix. And we talked about those before, so such as temperature. The higher the temp, the more something dissolves. Okay? The higher the pressure, which only impacts gases, the more it dissolves. Think about when I open a pop can, it goes that noise. What happens is all the gas that's dissolved, it comes out. Why? Because I've decreased the pressure. Amount of solute, say you're taking a nice relaxing bath, right? And you're putting some bath salts in there. Hopefully you're not eating them because that's really bad for you. Do not do that. But I'm putting bath salts in the bathtub. And if I kept adding them, there'd be a point where even though it's a bathtub, a ton of water, it would stop dissolving, right? The more solute that's getting dissolved, the less likely that it is to dissolve. And we'll see why for a minute, in a second here. So as you know, temperature impacts it, pressure impacts it. So does the nature or polarity. Okay, so those factors together move in. And this is what we see here. We have a high temp here. High temp means more energy. Particles are moving faster. I get faster dissolving. Here, colder, less dissolving. This factor of high temp also means I can usually dissolve more of something. There's exceptions to that though. But remember, the main idea is high temp is energy related, more energy. So think about it this way. If I was dissolving salt, just classic sodium chloride in water, it takes a certain amount of water, such as it shows here, 3, whether that's accurate or not, 3 waters for each sodium, each chlorine. Okay, that's what it says. Well, that means that there's a certain amount of water particles being quote unquote used up in order to dissolve this salt. And that means over time, there's not any more water molecules around to dissolve more salt. So the more and more salt that I add, the less likely it is to be dissolved because all the water molecules are being used up. Okay? And that's what I see here. These are 2 different salts. This is potassium nitrate. This is sodium chloride. And down here I have temperature. This is what a solubility curve looks like. And over here it says how much can be dissolved in grams. So let's say, right here at about 25 degrees, they can dissolve the same amount of solid. And that would be about 40 grams. And that's 40 right there. So about 40 grams can be dissolved in 100 grams of water, which is 100 milliliters. Okay. But as I double my temp to go to 50, okay, sodium chloride is still about 40. But the potassium nitrate has gone up to about 80. Okay, so different salts have different solubilities, right? So the higher the temp, the more I can dissolve. That's obvious here. But because the salts are different, they have different abilities to be dissolved. Okay, now imagine that you have 2 people that have been in swimming lessons, right? You don't just take a person who's brand new to swimming and chuck them in the deep end, right? That would be like this point. You have to have more experience before you can go into the deep end. And then different people have different abilities to swim. So even if I got more experience, maybe I don't improve that much in swimming. Okay? But some people, the more experience they get, or the higher the temperature, the more the higher depth of water that they could swim in safely. Okay, same idea. Now this graph is the opposite. As temperature goes up, I see these lines are going down. And the question I would ask is, what is different between these two things? Well, it's the substances, obviously. And if I were to look at helium, carbon monoxide, oxygen, or methane, maybe you could think of, okay, what are those things? When I think of oxygen, what do I think of? It's a gas. These are gases. So the higher the temp for gases, the less likely they are to dissolve in water. Think about it this way. You open a soda, you take a couple drinks, you put the cap back on, you put it in the fridge. Okay? That fridge has a lower temperature. It keeps the pop fresh. But if I were to put the same thing in my car in a summer day, it's going to get really hot, and that gas is going to leave solution. It's not going to stay dissolved. And that's because there's more energy, so that gas more easily escapes. So that's why if I want to keep a pop fresh for longer, I need to put it in cold temperatures. So really the only thing you need to know about solubility is how solubility changes as temperature changes. So if I looked at this graph and I'd say, what happens to the solubility of potassium nitrate, that's KNO3, as temperature goes up? You'd have to say, well, this line goes up, which means its solubility is increasing. Or what happens to the solubility of carbon monoxide, CO, as temperature goes up? Well, this line's going down, so it goes down. Okay. And you'd say, like, which of these has higher or a bigger change in solubility? Well, that would be potassium nitrate. The amount it goes up is different. And these solubility curves also give us more information, such as whether a solution is saturated, unsaturated, or supersaturated. And this is actually related back to that first video we watched week 1, where you saw that hot ice video. Those are supersaturated solutions, where there's more solid dissolved than I would expect. That would be any point above a line. So if I, example, dissolved at 100 grams of potassium nitrate at 20 degrees Celsius, that's more than I would expect to dissolve. I would only expect to be able to dissolve about 30 grams here. Well, that's called a supersaturated solution. And it doesn't really like to be in that situation. So that means if I disturb it, such as pouring out that liquid, solid forms really quickly. And that's what happened in those videos. It's related to solubility of a salt. And potassium nitrate would be an example, or sodium acetate is the one used in that video. Okay. Any point on the line. So if I had 100 grams dissolved at, let's say, on the line about 60 degrees, that would be saturated. That's, under normal circumstances, exactly how much you would expect to be dissolved. But if I had 100 dissolved at, let's say, 100, or let's say like 80, that's underneath the line. That means I could dissolve about that much more. It's called unsaturated. And that's really all you have to do there with those. I'm not going to ask you a lot of questions about these. I would really just know the definitions of them. And so interpreting graphs, the main idea is I can just go to temperature, go up to the line, and figure out how many grams are being dissolved. And that's really all you'll be doing with these. If you think Mr. Peters is the most confusing person on the face of the earth, you're not alone. But I would just watch this video here on solubility curves. That's another person explaining it. And maybe something they say, or the way that they say it, will be more helpful than this. And yeah, anyway, that's it for dilutions and solubility curves. So just try those couple extra bonus questions and then check your homework with the key. Tomorrow there'll be a short quiz. It's only 5 questions. And that's all we got. All right, guys, love you, miss you, and I will talk to you soon. Let me know if you have any questions. As they say, goodbye.